How's it going, my dudes? It's all right.
This is for you.
Oh my goodness, Alexis, you got to get out of jail free card here.
It's only
Only? That's the worst 15 minutes of the day. All right. Do you guys want to start with some questions from homework or whatever? If anybody has anything, we can do a little bit of that before we get going. If you don't have anything, that's okay. We can always deal with it later if something else comes up.
don't fully remember what we did last time because it's been a while.
That's okay. That's my job, not your job, right? Well, I mean, you do need to remember, but like, we'll kind of catch back up where we left off since it was like in the middle of a thought. Okay. 17. Sure.
We only went up to 22, right?
That sounds right.
What's a feedback question? Did you enjoy this?
All right. So 17 is a all on the calculator question. So it says to use your graphing calculator to classify the maxes and mins and find the maxes and mins. So 17 is x times, and then the square root is second, and the x squared button right here. And x minus 1. Just type it in exactly the way it looks. Okay, that looks fine. Hit graph. So this is my function. Right now it maybe does it. Do you think it does something else weird up here? Should we check just in case? Why not, right? I'll just make the x max 100 and the y max 100. Nope, it just kind of goes up forever, right? You cool with that? So I have, do I have any local mins or local maxes or global mins or global maxes with this? Yes! I have one global minimum. Where is it at? It's just this point right here where the graph starts. So that's the lowest point on the graph. That is the point 1, 0. And that is my global minimum. That's it. I didn't even have to really use the calculator to do it because I just could kind of look at the picture. Everybody's cool with that? Should be easy to see that 1 is the smallest value you can plug into here, because if you plugged in something less than 1, x minus 1 would be negative, and you can't square to negative. So that would certainly need to be the start. That's it. Okay. That's good, right? We didn't even, I mean, the picture helped, but I didn't even need to use the min and max commands. Yeah, you know, whatevs. All right. Anybody else? All righty. So last time we had been talking about inverses, and we had talked about how we can find the inverse for our function when the function is written as a mapping diagram. If our function is written as a mapping diagram, the domain and range basically just flip, and then the arrows go the opposite directions, right? So if f was my function in red, f inverse instead of sending 1 to 4, sends 4 back to 1. Instead of sending 2 to 6, sends 6 back to 2. Instead of sending 3 to 5, it would send 5 back to 3. Is that okay with everybody? And what we wanted to notice here was that if I did like f inverse of f of 1, what's going to happen here? Well, f of 1 sends 1 to 4, and f inverse sends 4 back to 1. So what has happened to 1 that we originally plugged in? Nothing, right? That's what an inverse needs to do. It needs to undo whatever the function was doing. So you just end up where you started at. Is that okay? We saw a second example that said, okay, if my function is a set of ordered pairs, how do I write its inverse? And that was quite easy. All we needed to do was transpose the x and y coordinates. So like negative 2, 4 becomes 4, negative 2. And I just do that for each one. I just swap the x's and y's and ta-da! There's my inverse. Pretty easy. And the last thing that we noticed was that, hey, in my first example, my inverse is a function, right? All of its domains got used, and each of those domains went exactly one place. But in my second example, the inverse wasn't a function because, hey, I have one domain that goes to 2 different ranges. 8 goes to 3 and 8 goes to 5. That's bad news for us. And we're left then with this question. Can I use f to predict when f inverse will be a function? Right? We've seen sometimes it might be a function, sometimes it won't be a function. Would it be nice to be able to look at f and know beforehand whether should be getting a function back or not? Yeah. And that's what we're going to build out and kind of do here today. Or take a pause here to build out and do. To do that, though, I need to need to define a couple of properties, and that'll give us what we need. Okay. So we're going to have 3 definitions here. So we say that a function is onto if every element in the range is mapped to by some element from the domain. And we'll do some examples here in a second to demonstrate what that exactly means. We say that a function is one-to-one if every element in the domain maps uniquely to a distinct element in the range. And then our third definition, we say a function is bijective if it is both one-to-one and onto. So let's take a little pause here and just kind of show you examples of what this really means. These properties one-to-one and onto and bijective. So this is an example of something that's not onto because one of the ranges isn't used. If all the ranges are used, it's onto. How many times can the ranges be used? As many times as you want to. As long as all of them get used, that thing would be considered onto. Maybe I'll write this up above. Everybody's okay with that? Okay. That'll come back in a second. There it is. So this example is not one-to-one because we have one range that's mapped to by more than one domain. The elements aren't mapped to distinct ranges. However, if I look at the second example, is this second example onto? Yeah, all the ranges get used. So this is onto. If I look at the first example, is that one-to-one? Yes, because each x has its own unique y, right? None of the y's are used more than once. So what does something that's both one-to-one and onto look like? Something like this. Every range is used, and each x goes to a distinct y. Everybody feel kind of okay about what we're saying here with one-to-one and onto? All right. Now remember the question that we're trying to answer here. How can I use f to predict when f inverse will be a function? So for a function f, we can say f inverse is a function if and only if f is bijective. So if I look at my function f, and that function is one-to-one and onto, then its inverse is going to be a function. Let's think about why that is a necessary condition to have both of those. So let's go back to these examples that we had up here. If I write its inverse, is that a function? No way, because not all the domains get used. So if I don't have onto, I'm going to, when I make my inverse, I'm going to run into not all the domains getting used. What happens if I didn't have one-to-one? Is that a function? No, because we have one domain going to two different ranges. So anytime we don't have one-to-one, when we make the inverse, we're going to have one domain going to more than one range, making it not a function. Remember, to be a function, you needed two things. You needed all the domains to be used, and the domains can map to only one range. So each domain has to go to just one place. Onto guarantees that the inverse will use all of its domains, and one-to-one is going to guarantee that the inverse will send each domain to only one range. Right? So we need to have both of those to guarantee that the inverse will be a function. Cool with that? Okay. So if I have a mapping diagram, it's easy enough to tell if something's one-to-one or not, right? What if I have a set of ordered pairs? Well, the onto-ness is just kind of like that's a given, right? Because the domain of f, or the range of f, is going to be exactly the y-coordinates, which are going to be exactly the domains for f inverse, right? So like, it's kind of automatic if you have a set of ordered pairs, you're going to have onto. Don't have to worry about that. What is one-to-one going to look like if I have a set of ordered pairs? What am I checking for if I'm looking for one-to-one? What am I really looking for? If I go back to my previous example here, it's the repeated y-coordinate that's going to show me that this was not one-to-one, because those repeated y's, when I make my inverse, become repeated x's. Everybody's okay with that? So those are two ways we've represented functions, mapping diagrams and sets of ordered pairs. Are those the common ways we represent function? No. What are the two most common ways we represent functions? The graph and an equation. So let's talk about those now, right? A little bit harder to see what's going on there than the mapping diagram and set of ordered pairs, where it's really easy to kind of see the properties at play and how to make the inverses. But let's look at something else here. So let's say we have this as my function, f of x, and I want to graph f inverse of x. Okay. What am I going to do that? Well, I'm going to take the ordered pairs that I'm given, flip the x and y coordinates, and plot those. So -2, 5, I'm going to plot 5, -2. 0, -3, I'm going to plot -3, 0. And 1, -1, I'm going to plot -1, 1. Now I just need to connect these 3 points together. How am I going to go do that? Here's the trick. This extrema is going to still be an extrema in the inverse. So like that's going to be the point furthest to the left. So there's my f inverse. Everybody can see that? Is that okay? Again, relatively easy to do, right? If you look at this picture, do you notice a relationship between f and f inverse? Or a symmetry between them? back. Let me try to do a better job there. They are reflections across the line y equals x. So like this part of f becomes this part of f inverse. You guys can kind of see that. It's a little bit more difficult, I think, to use your imagination to see that. But you could find the inverse graphically that way also. I would just assume find some ordered pairs and then swap the ordered pairs and connect everything back together again. But there's nothing wrong with just reflecting across the line y equals x also. That's okay to do. So I noticed that f of x here is a function, right? Is it onto? Yeah, every time we represent, this is driving me nuts, come on. Every time we represent our function with a graph, we can just assume they're onto. Is it one-to-one? No. How could I look at the graph of f of x and tell that it wasn't one-to-one? Well, it's easy to see that the same y coordinate gets used more than once, right? By the graph. What would we call this thing that we just did? It's like a horizontal line test. So I know that f of x is not one-to-one because we failed a horizontal line test. Because f is not one-to-one, what can I say about f inverse? It's not a function, right? Which is easy to see if I look at the graph of f inverse. Why can I tell f inverse isn't a function right away? Yeah, it fails a vertical line test. So the horizontal line test tells me if a function is one-to-one or not. And that result will tell me if the inverse is a function or not. Right? So I could say something in this case like, because f inverse fails a horizontal line test, it's not one-to-one. And since f is not one-to-one, f inverse is not a function. Everybody kind of catch that explanation there? What do we have to be really careful about when you're writing an explanation like that? Is your adverbs, right? Saying it is a bad idea. Say whether you're talking about f or f inverse, right? Like, it's not a function because it fails a horizontal line test, will not get full credit because I don't know what it is. Right? Because those are two different functions you're talking about if that answer is correct. They can't be both it. You know what I mean, guys? Okay. But what is really the most common way we represent a function? It's usually not with a graph. It's with an equation. So let's say we have this equation and we're looking for its inverse. So the first thing I want to do is replace my function notation with just y equals. Then I want to get the x by itself. And we're going to swap the names for x and y. Then we're going to replace y with f inverse of x. So those are my steps to find the inverse. Which of these steps is the most challenging one? It's getting x by itself. Okay, so first thing I do is I'll replace the f of x with a y. Tough. Now, to get the x by itself, essentially what I'm doing is the solving for x steps, right? So remember the order of operations. We go parentheses, exponents, multiplication, division, addition, subtraction when we're simplifying. But when we're solving, we're undoing in the opposite direction. So the first thing you'd want to do is undo addition, subtraction, then undo multiplication, division, et cetera, et cetera, et cetera. Okay with that? All right, so getting x by itself, what's the first thing I want to do in this specific instance? Add 7 to both sides. Good. Yep, that's right. Next, what should we do? Divide by 3. So dividing by 3 on both sides is the same as writing the 3 over both of them or the 3 over each individually. Either is okay. I like to write it over the whole thing. Everybody's okay there? X is now by itself. Correct? Step 2 is done. The next thing it says is to swap x and y. So everywhere there was an x, I'm going to write a y, and everywhere there's a y, I'm going to write an x. Step 3 is done. And the last thing I do is just instead of writing y, I'm going to write f inverse. And I'm going to write that on the left-hand side so it looks like kind of the standard way that we write things. Any questions so far on what we did there? Let's check. How do I check if two functions are inverses if I've written them as equations? Not plugging in numbers isn't going to be enough because you'd actually have to check that it undoes each other for every number. And since there's an infinite number of things you can plug in, you'd never finish doing that, right? We have to be a little bit more general than that. So we had a theorem from last time that said that f and g are inverses if and only if f compose g of x equals g compose f of x, which is equal to x. It's this that I'm going to use to show that to check that these two things are inverses. So we'll do f of f inverse first. So remember, f inverse in our case is x plus 7 over 3. When I plug that into f, everywhere there was an x, I'm going to put in the x plus 7 over 3. So f was 3x minus 7. So instead of the x, I'm just going to write the big parenthesis. And then inside big parenthesis, I'm going to write in f inverse. So x plus 7 over 3. Now all I need to do is try to simplify this down. The answer I should get is just x. Since I'm simplifying, what should I do first? The multiplication division, right? Notice I have a times 3 and a divides by 3. So those can cancel out. Since all the multiplication division is done, I could drop the parenthesis there. Next, I can add the 7 and subtract the 7. And I'm left with just x, which is what I need. Now I have to check the other direction. So I need to do f inverse of f of x. So f inverse is, I'm going to replace the x's with a big parenthesis. And then inside big parenthesis, I'm going to write f, which is 3x minus 7. Everybody's okay with how I did the compositions there? Now I need to simplify this expression. I'm looking to get x at the end. What should I do first? Is there any reason that parenthesis needs to be there? Is anything being multiplied to it or divided to it, specifically to just that parenthesis? No. So those parentheses don't need to be there. So I would work in the numerator first and do the minus 7 and plus 7, cancel out. And then I have the times 3 and divides by 3, cancels out. And I'm left with just x. Right on, my dude. We did it. Definitely inverses. Everybody cool with that? Do you have to do this? Not unless you're asked to by the direction. But I believe there are some problems in the homework where I give you two functions and ask you to show me that they're inverses. This is the process you should do. Let's do a couple more examples because this is some good algebra review, right? Specifically, this getting x by itself parts. It's been a little while since we've done any of that stuff. Okay, so let's say we have this function, g of x equals 2x plus 5, divided by 5x minus 8. The first step, same as before, is to replace the function notation with a y equals. And now we need to get the x by itself. What should I do first here? This is a little tricky, right? What's trickier about this one than the previous one? Yeah, we have x in more than one place, right? What do you guys think? Anybody with a guess? I want to be clear that it's okay to just take guesses at stuff. It gives me an idea of what your intuition is, and then gives me an opportunity to tell you whether what you're thinking was okay or not, and explain why or why not, so that hopefully you can remove that as something you'd want to do. So it's definitely okay to volunteer to just take a guess at something, even if you don't know, right? I just want to be honest that it's a good thing. It's helpful for all parties involved. Now, you don't have to. I'm not trying to guilt anybody into taking a guess here. But I just want to let you know that, like, there's no penalty. Even if I'm like, wrong, I'm going to do it, like, good-spiritedly with a smile on my face, right? We're just trying to have some fun. But there's no penalty for being wrong in this sort of situation, right? Okay, so first thing I would want to do is get rid of the fraction part, right? This would be easier if there's no fraction involved. What can I do to get rid of the fraction? Multiply by 5x minus 8. So that's going to distribute through. Is everybody okay with how I got to that? Take a minute and process. If you have an issue, let me know and we can explain a little bit more. All right. What should we do? What should I try to do next? If you could see the screen, because it didn't cut out on me. I still have the same problem I started with, though, right? Is that I have x in more than one place. Everybody agree? We're trying to get the x by itself. The next thing I'd want to do is get the things with x's on one side and all the things without x's on to the other side. So to do that, I can subtract 2x from both sides. And then add 8y to both sides. Everybody okay with what I did there? Woo! Excuse me. Maybe we'll write that down. There. Still have x's in more than one place, though, right? How can I get x's in two places and turn that into an x in one place? This is an Algebra 1 skill. It starts with the letter F. Factoring, right? And what kind of factoring specifically are we going to be doing here? Just the greatest common factor. If I look at 5xy and then minus 2x, both of them contain a common factor of x. So I'm going to just factor that out. And now I have x in just one place. Oh, okay. That's nice. And now to get that x by itself, I would divide by 5y minus 2. Right? Just whatever it's being multiplied by. X is by itself. Good for us. No, now we swap the x's and y's. Well, it's all the hard stuff we need to do. Right? That's easy, swapping x and y. And then we rewrite, instead of y, we're going to write f inverse. Oops, not f though. What letter did I use here? G inverse. Let's be consistent. It's confusing for everybody if I start just changing the letters all willy-nilly. Is that okay? Now that one was a bit more complicated algebraically, right? Good thing we did an example to remind ourselves like how to deal with something like that. Because most people don't remember this factoring trick, right? That's something that typically you're not thinking about because it was a long ago that you did stuff like that. Which is part of why we do the examples, right? All right, what do you think we're going to do next? Let's check them. Yeah, Luke's making some faces like this is going to be ugly. Well, a little bit. What makes this kind of ugly? Well, we have a fraction, but we also have x's in more than one place. So like when we do our plugging in, it's gonna get a little bit crazy. So g was 2x, and in place of x, I'm gonna put the big parenthesis, plus 5 over 5x, but instead of x, I'm gonna put the big parenthesis, minus 8. Now, in place of big parenthesis is going to be G inverse. You guys like how I do the composition where I write out the thing with the blank and then plug the stuff in? I think that's often a helpful way of like thinking about it. But what in the heavens do I have here? This is like a fraction with fractions inside of it. Everybody see that? The name we call this thing, this is called a complex fraction, when we have fractions inside of fractions. It's like inception for fractions. Fracception? I don't know. Is Inception still a movie people care about? Probably not, based on the blank stares I'm getting from you guys. Well, it's a pretty big movie, like, I don't know, I guess it's probably been 10, 15 years now, huh? Not so cool anymore. All right. What in the world do I need to do to simplify this mess? The first thing I'm going to want to take care of is the fractions inside of fractions part, right? If If I can get this down to just like something over something, that would be quite helpful. Everybody agree with that? So I'm going to look at all the fractions I have and look at the least common multiple of the denominators. What are the denominators that I have? I have 1, that's the denominator on the 5 and the minus 8. And then I have 5x minus 2. Everybody agree with that? What's the least common multiple of 5x minus 2 and 1? 5x minus 2? Everybody agree with that? So I'm going to multiply the top and bottom of this fraction by 5x minus 2. Why am I allowed to just do that? What's 5x minus 2 divided by 5x minus 2? 1. And 1 times anything is itself. So have I done anything to change this fraction? Just the way it looks, right? I haven't changed the value of it, though, at all. Everybody agree with that? It's like taking 1 and writing it as 4 over 4. Just looks different. It's changed its clothes. It's still 1. Everybody cool? Okay. So when I multiply, these things have to distribute in. Everybody's cool with that? When I multiply 5x minus 2 to the fraction 8x plus 5 over 5x minus 2, the 5x minus 2's cancel. And then I multiply to the plus 5. I'm just going to write it like that for now. And the same thing happens in the denominator. And look at that. That's lovely, right? We now have only a single fraction. There's no fractions inside of fractions going on. Yes. That's really nice. What should I do next? Distribute. Absolutely. What's the place that I need to be a little bit careful when I'm doing this distributing? In that denominator, when I distribute the negative 8, I have to make sure that I remember to take the negative sign with it. Oh, yeah. And whoa, look at this! When I combine like terms in the numerator, notice that I have a plus 10 and a minus 10. And in the denominator, I have a plus 40x and a minus 40x. Whoa, those are going to cancel out. To give me 41x over 41, which reduces to x. Yes! Did it. Who feels brave and strong now after that? You do! Awesome!
Oh,
I'm just joking. Matt, go
I
ahead.
have 2 questions actually.
Yeah, go ahead.
For that last part, could you just like plug it like in the calculator or no? Like, is that an easier way to do it?
Well, you can't because of the x's,
Oh,
right? So your calculators that you guys have don't do symbolic algebra. They can only do numeric.
Okay,
So because of the variable stuck in there, there's nothing the calculator's not really going to help you on that.
alright, and then can I use that?
Certainly. Elise.
So you know how on the example before this, I don't know if we're done, but we checked it with like both.
We do have to do the other direction here, and I was.
Have to.
Mhm.
Okay.
I know. I know.
Can I use the register?
It's like I need a break on that. Yes, go ahead. So as Elise was asking, we do need to go the other direction. Oh no, Mr. Kulik, are you joking? No, I'm not, unfortunately. But here's the good thing. It's not a joke. No, I mean, like it's a joke that I have to do it like this is like life is a joke kind of. It's like a joke like that. Like a depressing, like, no, it's not a joke, and that's the joke he's not joking.
Yeah, it's a joke, but it's really not.
Yeah, and that's what's funny about it is that it's not. And it just. So just like before, can you write I'm sorry? No.
I said I'm gonna write I'm sorry.
No, don't.
Yeah, I'm gonna need to do like 6 of these before I understand.
Yeah, and that's this is like what you're doing right here is not trivial, right? This isn't trivial. This isn't easy. This is the first time you're doing it. Ideally, you would have done stuff like this last year, but you didn't.
No, I probably have. I have really bad memory.
Yeah, doing some more practice will get that kind of jogging along. And they're not all this difficult. It's this example, or this type of example in particular, that is quite tricky. Here's the good news, though, is that they're all kind of the same. So to simplify this, what should I do? Hang on tight to those. They're expensive. They're actually drop tested, so they're like shouldn't break unless you really kind of like get aggressive with it. I think they're like drop tested up to like 10 feet. Supposed to survive. But you catch a corner or something, and who knows, you might crack the screen or something. But they're pretty rugged. So don't panic. But try not to drop it. Like, don't press your luck, right? That's g of x. That was the original problem. If you go all the way back up to here, that's what g of x was. Okay, come on, computer. Come on. Okay, so we did the composition. How do I get rid of the fractions inside of fractions? Multiply by? Excellent. We'll distribute that through. And hopefully you're already noticing that like doing it the second time feels a little bit more comfortable. Everybody good there? What do I do next? Distribute. And now that we've distributed, what do you notice? And you get 41x over 41 again. Hey, that looks familiar, doesn't it? Okay. Next up, another example. Let's see, I think we're on the letter H, right? Now what comes after G? I think so. That alphabet's always kind of sketchy, though. C, E, F, G, H. Yeah, H is next. What do I do first? Looking to find the inverse. Replace f of x with y, or in this case, h of x. Okay. Then we need to, well, that's embarrassing.
Is that me?
I don't know who it was. I wasn't talking to you specifically, I was just talking about in general, like. Okay. What do I do after I've done that? Get the x by itself. To do that, what should I do first? Add the 4. I love it. Then what? Divide by 3. Even better. Now what? What? Somebody whispered it. Square root both sides, yeah. When we square root both sides of an equation, what do we need to remember? Plus or minus. Awesome. Yeah, I love it. Paying attention. And guess what? The x is by itself. So we can just swap the x's and y's and rewrite this as, instead of y equals, h inverse. Quick note here, is h inverse a function? Take a look at that. Is that a function? No way. What's wrong with it? How can I look at that and tell it's not a function right away? The plus or minus, yeah, exactly right. So any x value that you can plug in and take the square root of is going to give you two y values, the positive and the negative. So what does that tell us then about h of x? It wasn't 1-to-1, right? Take a look at the equation for h of x. What type of function is this? I know you did this last year, because it's like the only thing you did last year. It's all a blur. It starts with a Q, quadratic. Very good. And what does the graph of a quadratic function look like? What's the name of that shape? Starts with a P? Yeah, parabola. So that's what your graph looks like. And clearly, h of x is failing a horizontal line test. So that means it's not 1-to-1, which means h inverse is not a function. Everybody cool with that? What if we wanted h inverse to be a function? And maybe we want to say even stronger than want. If we needed what should we do if we need h inverse to be a function? Well, we're going to restrict the domain of h so that h is 1-to-1. So if I look at h, I either want to keep that half of h or that half of h. Does it matter which half I keep? No, it does not matter. Which half would you keep, the yellow or the green? I'd keep the green. Why the green? Because all of those x's are positive. That allows me to get rid of a negative sign a little bit later on. So here we can have that same problem, but say that our h of x's, or I'm sorry, our domain is just from 0 to positive infinity. So what does my graph look like now? It's going to look just like half of a parabola. Everybody's okay? This is equivalent to saying x is greater than or equal to 0. So if I do the same steps as above, I'm going to end up with plus or minus y plus 4 over 3 is equal to x. Right? But I know x has got to be greater than or equal to 0. So what can I do then with the plus or minus? If x equals plus or minus the square root of yada, 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 but I know x has to be greater than or equal to 0, what can I do with the plus or minus? Get rid of the minus, right? If x has to be greater than or equal to 0, x can't equal plus or minus something, x can't be minus. Right? Because minuses aren't greater than or equal to 0. And then yada, yada, yada. there's our answer with, ugh, good gravy. Which we notice is a function. Now, why is Mr. Kulik going through and showing you this, like, seems like pretty ticky-tacky thing, right? It's like, oh, this is like why? Like, okay, so you want the inverse to be a function, but like, why? Right? Like, who cares? I don't. Well, here's the reason. Later in this semester, we're going to talk about the trig function, sine, cosine, tangent. And we're going to talk about the inverse trig functions, sine inverse, cosine inverse, tangent inverse. None of sine, cosine, and tangent are one-to-one. So when we create their inverse functions, we're going to have to restrict their domain. Just like we've done here in this example, to create these inverses so that the inverses are functions that we can type into our calculator. However, as a result of restricting their domain, there's a bunch of adjustments we have to make when we use our calculator to actually get the answer we're looking for. So I like doing this example here because we end up doing the same thing and having to deal with the consequences of doing this restriction later on. Okay? Okay. This feels like the place to stop. I think at this point we can do a whole bunch of problems now. I know I'm excited too. We can do all the way up through 31 to 51, and then 53 to 55. We're skipping those log ones. As a heads up, this is the last. So this is the new stuff. This is new today. From last week, we still had 23 to 30 that I hadn't checked for yet. So all of this will be for Sunday. Does that clear up? Okay. This was the last section that we're covering in chapter 1. What does that mean?
We have tests next week.
Test coming up, right? When would we expect this test?
Next week.
Next week. We're going to do a review day next time, Thursday, right? Friday, whatever, the next time we have class. And we'll be taking a test the following class period after that. Okay? Everybody cool? I think all that stuff, all the dates for those are up on My Notre Dame. Okay? And we'll do more questions and stuff next time.